Have you ever wondered, what is everything made of? What is it that's holding us together? Your first thoughts may be, well, particles, right? But what particles? How many electrons are there? Protons and neutrons? All of it is matter. Everything you will ever see in your life is made up of matter. While it's true that everything you will ever see is made up of matter, matter only accounts for 5% of the known universe. That means 95% of the total contents of the universe is made up of something we cannot see or detect. What could this be? Step forward. Dark matter. In short, dark matter is matter which is completely undetectable to us, hence why I refer to it as dark. It emits no light or energy. Dark matter does not interact with the electromagnetic force, and this non-interaction means that it is not detectable by any methods at all, neither infrared, microwaves, nor gamma waves, not even radiation. It is believed that this undetectability is due to a secret which lies within its composition. However, as of now, we are unsure what this is. This does not mean that this type of matter is invisible. Matter has never in any instance just disappeared. This means dark matter needs to be something else entirely. Visible matter, as you know, consists of particles such as protons, neutrons, and electrons. We call this baryonic matter. We're not sure of what dark matter is made of. It could be baryonic, like visible matter, but also may well be non-baryonic. Though the leading theory is that dark matter is composed of non-baryonic matter, the lead candidates are WIMPs. No, these are not a bunch of easily frightened nerds, but what we call weakly interacting massive particles. Yes, that's right. Even though these particles are undetectable, they are believed to be massive. WIMPs are believed to be much more massive than regular particles, approximately 100 times the mass of a proton. But due to their weak interactions with normal matter, WIMPs are notoriously difficult to detect. Examples of these include neutralinos. These are particles which are more massive and move a bit slower than neutrinos, and are a strong candidate for dark matter. However, even these are just hypothetical and yet to be found. And the opposite of a weakly interacting massive particle is also believed to exist. This would be the strongly interacting massive particle, or SIMP. Another dark matter candidate is sterile neutrinos. Neutrinos are subatomic particles which are very similar to electrons and rarely interact with normal matter. Neutrinos come from the sun, but due to the fact that they hardly ever react with normal matter, they just pass through Earth and everything on the planet. Sterile neutrinos are only believed to interact via gravity and not any fundamental interactions. Though, like neutralinos, they are also hypothetical. These join the long list of other hypothetical particles, such as gravitons, particles responsible for gravity, tachyons, which are particles that experience time backward, and axions, which are particles that have both a low mass and low energy. These are also prime dark matter particle candidates, but, like the rest, are yet to be found. Why do we think dark matter exists? Taking into consideration of everything we have discussed so far, an important question arises. If we cannot see or detect dark matter, how do we even know it exists? Well, the answer, like a lot of times in physics, is gravity. It has long been hypothesized by physicists that the universe should have more matter than we can detect. Why? Because the gravitational forces that seem to be present in the universe are thought to be stronger than baryonic matter alone would result in. In the 1970s, astronomers observing spiral galaxies found something that they didn't expect to find. Initially, it was thought that the material within the center of these galaxies would be moving at a faster rate than the material in the outer edges. Instead, they found the stars in both locations traveled at the same velocity, indicating the galaxies contained more mass than could be seen. Studies of gas within elliptical galaxies also indicated a need for more mass than found in visible objects. The key takeaway from these observations was this: clusters of galaxies would fly apart if the only mass they contained was the mass visible to conventional astronomical measurements. That's what the math told us. So for these clusters of galaxies not to just fly apart and remain as they are, there must be more mass, the mass that we cannot see or detect. And as a result, came the idea of dark matter, matter that we cannot see or detect. Albert Einstein showed in the early 20th century that massive objects in the universe bend and distort light due to the force of their gravity. The phenomenon is called gravitational lensing. Gravity doesn't only affect large objects made up of matter, but also light itself. And by studying how galaxy clusters distort light, astronomers have even created a map of dark matter in the universe. The majority consensus in the physics community is that dark matter does indeed exist. And though we can't see it, we can see its effect and galaxies. Although the evidence points towards the existence of dark matter, there is a chance that no such thing exists after all, and that the laws of gravity describing the motion of objects within the solar system requires revision. It seems that dark matter is spread through the cosmos, almost like a net. Galaxies form at the intersection of the net's fibers. In short, dark matter is everywhere. We're surrounded by it. But the question is, where did this all come from? The simple answer is that we don't really know. But scientists have a few theories on its origin. A 2021 study that was published in the Astrophysical Journal suggested that black holes may be a source of dark matter. This implication comes from a model created by astrophysicists at Yale and Miami University in collaboration with the European Space Agency. The initial model seemed to suggest that primordial black holes created in the very early universe may account for all of the dark matter in the universe. These black holes varied greatly in size, from ones that were the diameter of the head of a pin, and also supermassive ones, several times larger than the Sun. Though the primordial black holes that are candidates for dark matter are believed to be only asteroid to moon-sized. But how would these black holes even form when there are no stars in the very early universe, as the black holes we know of all form from the gravitational collapse of very large stars? Well, firstly, these black holes must be non-baryonic, but also be comprised of some sort of matter. Therefore, a leading candidate for this is dark matter, a form of non-baryonic matter. As such, dark matter must have been created during the Big Bang, like all normal matter in the universe. However, there are many arguments against this theory of primordial black holes explaining dark matter. One such argument is linked to the sheer amount of dark matter that should be within our universe. It is generally accepted that primordial black holes couldn't possibly make up all of the dark matter given the current constraints, because, well, there should be too much of it. Though it has been proposed that most of the remaining dark matter could be contained inside white dwarfs, neutron stars, and failed stars, the so-called brown dwarfs. However, the majority of scientists accept that black holes cannot be made up of dark matter. Why can't they? Well, the answer lies in the other forces other than gravity. Phenomena such as friction and collisions rely to some degree on the electromagnetic interaction. Normal matter undergoes these electromagnetic interactions. Dark matter does not. This has a huge effect on what the matter can and cannot do. Though this theory may explain where dark matter may be concentrated in our universe, it doesn't quite explain how it got there in the first place. The obvious answer to this would be the Big Bang, as nothing existed before it. But in the case of dark matter, physicists believe it is a thermal relic, and a huge amount of it was created before the universe was even a second old. In the very early universe, everything was so hot that particles were being produced from photons smashing into other photons, photons hitting electrons, and electrons hitting positrons and producing very heavy particles. The entire cosmos was just a huge amount of particles just colliding with one another. This period lasted only 1/1,000,000,000th of a second. Then came what we call the freeze-out. The freeze-out caused the universe to expand and cool to the point where particles became less energetic, and so the collisions became less frequent and less catastrophic. One of these massive particles floating through the universe is finding fewer and fewer antimatter versions of itself to collide with and annihilate. Eventually, the universe would get large enough and cold enough that the rate of production and annihilation hits zero. These particles would eventually have no antiparticles to annihilate and end up just floating through space, interactionless. This would be dark matter and would be abundant in vast amounts. As of now, these are just theories put out to provide some possible explanation as to how dark matter could possibly exist. We won't be able to provide a more concrete explanation for its origin until we actually detect any dark matter particle. So the question is, if dark matter doesn't interact with anything, what is its purpose, its role on the vast stage we call the universe? Is it just there as a mathematical placeholder so that scientists can sleep at night? When a galaxy forms, it consists of both dark matter and normal matter at a ratio of 5:1. And as is the case for all matter, dark matter particles are attracted to the center of the galaxy due to the force of gravity and accelerate towards that direction. But that's where the similarities between normal and dark matter end. Dark matter travels through the galaxy and has no collisions or friction, doesn't undergo any heating, has zero interaction with electromagnetic radiation, and there is no exchange of energy or momentum with the other particles. It begins and will remain on a slow, high angular momentum orbit, taking perhaps 1 billion years or so to make a single full ellipse. Normal matter sheds momentum and angular momentum and sinks to the core of the galaxy, where it clumps together, while dark matter always remains distributed in a halo around the galaxy, unable to shed linear or angular momentum. Normal matter forms individual, dense, small-scale clumps. Dark matter can only form sparse, diffuse clumps, mostly on very large scales. Without a mechanism by which it can shed angular momentum, dark matter can never even approach the densities necessary to create an event horizon and hence a black hole. There is no such thing as a dark matter star, so you can't have dark matter undergo core collapse. There are no regions that ever collect enough dark matter to pull light within that region back on itself, meaning that you can't have dark matter undergo direct collapse. And there are no stellar remnants or other comparably dense objects made out of dark matter, meaning that there's no way to have a collision between dark, matter-rich entities. Dark matter seems to just exist and doesn't make up any detectable larger structure, unlike normal matter. However, once we actually do have a black hole, there's no reason dark matter particles can't cross over the event horizon and add to the mass of the already existing black hole. Dark matter is no different than any other form of matter or radiation in this regard. If you cross over the edge of the event horizon, you will inevitably fall to the central singularity and wind up adding to the overall mass of the black hole. But because of the clumpy nature of normal matter and the diffuse nature of dark matter, there are no realistic scenarios in which even 1% of a black hole's total mass could come from dark matter. For black holes, it's normal matter or nothing. In fact, based on what we understand about dark matter and the universe, there's only one possibility of ever creating a black hole made of dark matter, and that is, as we have discussed previously, primordial black holes. Ones that were formed during the very early universe may have very well been made up of dark matter. But even then, these black holes would be very small and would be more likely the seeds for much larger black holes scattered across the universe. When it comes to dark matter as we understand it, one can fully expect that there will be no black holes in the universe, today or ever, made either primarily or exclusively of dark matter. There are no stars, supernovae, stellar remnants, or direct collapse scenarios that could possibly have led to any detectable structures made of dark matter. So that's that. Dark matter is just undetectable particles scattered all over the universe that make up nothing. However, dark matter can interact with light in an interesting way. Very high concentrations of dark matter can act like a lens to bend light and drastically alter the appearance of background galaxies seen from Earth, stretching them into arcs or splitting them into multiple images of the same object on the sky when observed via a telescope. So how can we study something that we can't even detect let alone see. There are two main methods to study dark matter. Astrophysicists study how dark matter is distributed across the universe, and they do this by observing the clustering of material as well as the motion of objects. Meanwhile, particle physicists are aiming to detect the particles that make up dark matter. An experiment mounted on the International Space Station called the Alpha Magnetic Spectrometer detects antimatter in cosmic rays. Since 2011, it has been hit by more than 100 billion cosmic rays and has measured an excess of positrons, the antimatter counterpart of an electron. Researchers aren't sure where this abundance has come from, but one idea that has gained support from the scientific community is that this abundance is due to dark matter. Though more data is needed to make sure this is indeed from dark matter and not from some other unusual occurrence. Back on Earth, beneath a mountain in Italy, the LNGS Xenon 1T is hunting for signs of interactions after WIMPs collide with xenon atoms. The Large Underground Xenon Dark Matter Experiment, or LUX, seated in a gold mine in South Dakota, has also been hunting for signs of WIMP and xenon interactions. Though so far, both of these have fallen short of finding the elusive matter, and we are not yet close to finally confirming the existence of dark matter. Dark energy is something else that, like antimatter, is confused with dark matter. We could make an entire video on dark energy, but we'll go over it briefly here. Several decades ago, physicists found evidence that the expansion of the universe was not slowing down. This was certainly unusual, as the only thing that could make a moving object increase in speed is energy. Instead, the universe's rate of expansion was increasing. Some sort of energy had to be at play here. That energy was dubbed dark energy. Called dark, as it must be very weakly interacting with all matter in the cosmos, if at all. Dark energy acts as an opposite to gravity, and is thought to be the key factor at play in increasing the rate at which the universe is expanding. However, it is theorized that dark energy contributes almost 70% of all the energy in the universe. And even though dark energy constitutes the majority of the available mass energy in the universe, its underlying nature has remained elusive for decades. Dark energy has no real connections to dark matter beyond sharing the word dark, which just means that scientists don't really know what these things are. So to sum up, dark matter is an undetectable type of matter, though it is believed to be 5 times more abundant in the universe than regular matter. It is not antimatter, which is detectable matter but with opposite charges to normal matter, and it isn't dark energy, the driving force behind the universe's increasing rate of expansion. Dark matter can't make up any detectable structures, unlike normal matter. Dark matter is sort of just diffusely scattered across the cosmos. Will we ever detect dark matter and confirm its existence? Probably not. Thank you for watching. Don't forget to subscribe, like, and leave a comment with topics we could cover in later videos.